Quick question. What shape is the Earth? If you said a sphere, you're wrong. If you said an oblate spheroid, you're closer, but still wrong. And if you're one of those people who thinks it's flat, well, we need to have a serious conversation. The real shape of Earth is so complex, so irregular, and so constantly changing that scientists needed to invent an entirely new word just to describe it. They call it a geoid, and it's one of the most fascinating and misunderstood aspects of our planet. Here's what's going to blow your mind. Earth isn't even the same shape from day to day. Right now, as you watch this video, our planet is bulging, contracting, wobbling, and deforming in ways that would make your head spin if you could see it happening in real time. The ground beneath your feet rises and falls by several centimeters twice a day. The entire planet expands and contracts with the seasons. Mountains are slowly sinking. Ocean floors are rising. Nothing is stable. Over the next hour, we're going to explore the true shape of Earth, and I promise you, it's far stranger than you ever imagined. We'll use precision satellites, gravity measurements, and cutting-edge science to reveal a planet that's lumpy, asymmetric, and constantly morphing. We'll destroy flat Earth claims with simple observations you can make yourself. We'll discover why Earth bulges at the equator and what that means for athletes trying to break world records. We'll explore how gravity shapes our planet in ways that defy common sense. By the end of this video, you'll never think about our planet the same way again. So let's dive in and discover Earth's real shape, finally revealed. Before we can reveal Earth's true shape, we need to address the elephant in the room: flat Earth theory. Despite overwhelming evidence, a surprising number of people still believe the Earth is flat. So let's settle this once and for all with observations you can make yourself. The shadow that proved everything. In 240 BCE, a Greek mathematician named Eratosthenes performed one of the most elegant experiments in scientific history. He heard that, in the Egyptian city of Syena, modern-day Aswan, the sun shone directly down a well at noon on the summer solstice, casting no shadow. But in Alexandria, 800 kilometers to the north, vertical objects did cast shadows at that same moment. Eratosthenes realized this could only happen if Earth's surface was curved. On a flat Earth, the sun would create the same shadow angle everywhere. But on a spherical Earth, the sun's rays would hit different locations at different angles. He measured the shadow angle in Alexandria at 7.2 degrees, which is 1/50th of a full circle. Multiplying the distance between the cities by 50, he calculated Earth's circumference at about 40,000 kilometers. The actual circumference is 40,075 kilometers at the equator. He was off by less than 2%, and this was over 2,200 years ago, without any modern instruments. You can repeat this experiment right now. Find a friend who lives several hundred kilometers directly north or south of you. On the same day, at the exact same time, both of you measure the angle of a shadow cast by a vertical stick. If Earth is flat, the angles will be identical. If Earth is curved, they'll be different. Spoiler alert, they'll be different, and you can use the difference to calculate Earth's curvature yourself. Ships disappearing over the horizon. Here's another observation anyone near a large body of water can make. When a ship sails away from shore, it doesn't just get smaller and smaller until it vanishes into a distant point. Instead, it disappears from the bottom up. The hull vanishes first, then the midsection, and finally, the mast. This happens because Earth's surface curves away from you. On a flat Earth, the entire ship would remain visible, just getting smaller with distance. The fact that it disappears bottom first is direct visual proof of curvature. Sailors have known this for thousands of years. It's why crow's nests on ships are built high up, to see farther over the curve of the ocean. You can enhance this observation with a telescope or binoculars. As a ship disappears over the horizon to your naked eye, zoom in with optics. You won't bring the hull back into view. Why? Because it's physically blocked by Earth's curvature, not by distance or atmospheric effects. The Bedford Level Experiment. Flat earthers often cite the Bedford Level Experiment from 1838, where a 6-mile stretch of canal appeared flat to observers. They claim this proves Earth is flat. What they don't tell you is that this experiment has been repeated with proper controls, and it actually proves the opposite. When you account for atmospheric refraction, which can bend light and make distant objects appear higher than they actually are. And when you use proper surveying equipment, the Bedford level clearly shows Earth's curvature. Over 6 miles, there should be about 24 feet of drop due to curvature, and careful measurements confirm this. In fact, a YouTuber named Soundly did a brilliant recreation of this experiment with modern equipment, and the results unambiguously showed Earth's curve. The original flat Earth interpretation failed to account for basic optical physics. Time zones make no sense on a flat Earth. Here's something ridiculously simple that flat Earth models can't explain. Time zones. When it's noon in New York, it's 9 a.m. in Los Angeles, 5 p.m. in London, and 1 a.m. the next day in Tokyo. Everyone experiences day and night in a predictable pattern as Earth rotates. On a flat Earth with the sun circling above like a spotlight, there's no configuration that produces what we actually observe. If the sun is above the North Pole, everyone should see it, just at different angles. You can't have half the world in darkness while the other half is in daylight if we're all on the same flat plane looking up at the same Sunday. Flat earthers try to solve this with increasingly absurd explanations involving perspective, local suns, or mysterious atmospheric properties that somehow make the sun invisible. But none of these hold up to even basic scrutiny. A spherical Earth rotating in front of the sun explains time zones perfectly, simply, and completely. Star trails and navigation. If you've ever taken a long exposure photograph of the night sky, you've seen star trails. Beautiful circular arcs created as stars appear to rotate around a central point. In the northern hemisphere, stars rotate around Polaris, the North Star. In the southern hemisphere, they rotate around the South Celestial Pole. Here's the kicker. Observers in the northern and southern hemispheres see completely different sets of stars rotating in opposite directions around different points. This is impossible on a flat Earth where everyone is looking up at the same sky. On a spherical Earth, it makes perfect sense. Northern observers look toward the North Celestial Pole, southern observers look toward the South Celestial Pole, and they're looking in fundamentally different directions because they're standing on opposite sides of a sphere. Navigators have used this for thousands of years. The altitude of Polaris above the horizon equals your latitude in the northern hemisphere. This only works on a spherical Earth. On a flat Earth, Polaris would appear at the same angle from everywhere. Flights and navigation routes. Commercial flight routes provide another nail in the flat Earth coffin. Look at flights in the southern hemisphere, say from Sydney to Santiago, Chile. On a flat Earth map, where the North Pole is at the center, these cities are on opposite edges of the disk, requiring a flight over North America or Europe. In reality, the flight takes about 1-2 hours and flies directly over the Pacific Ocean and Antarctica. How? Because on a spherical Earth, this is the shortest path. The flight routes used by airlines match perfectly with what you'd expect on a globe and make no sense on a flat plane. Even better, you can track these flights in real time online. Websites like Flight Radar 24 show you the exact paths planes take, and they all match the spherical Earth model. No conspiracy theory can explain why tens of thousands of flights every day, operated by thousands of different airlines, in hundreds of countries. All follow routes that only make sense on a globe. Gravity, the force flat Earth can't explain. Perhaps the most fundamental problem with flat Earth theory is that it can't explain gravity. We know gravity exists. We experience it every moment of every day. We can measure it. We can calculate its effects with extraordinary precision. Gravity pulls objects toward the center of mass. For a spherical Earth, that's the center of the planet, creating a force that pulls down equally from any point on the surface. On a flat Earth, gravity would pull toward the center of the disk, meaning people near the edges would experience gravity pulling at an angle, not straight down. Standing in Australia would feel like standing on a steep slope, with everything sliding toward the North Pole. Flat Earthers sometimes claim that objects fall due to density or buoyancy, not gravity. This is nonsense. Density and buoyancy are properties of matter that help determine how objects move under the influence of gravity, but they don't create downward force by themselves. In the vacuum of space, where there's no air for buoyancy, objects still fall toward massive bodies. The Apollo astronauts dropped a hammer and a feather on the moon, and both fell at the same rate, proving gravity works in a vacuum. The final nail. Photographs from space. We have thousands of photographs and videos of Earth from space, taken by multiple countries, private companies, and individual satellites. They all show the same thing: a beautiful blue sphere floating in the darkness. Flat Earthers claim these are all fake, part of a massive global conspiracy involving NASA, Roscosmos, ESA, CNSA, ISRO, SpaceX, Blue Origin, and dozens of other organizations, plus thousands of individual scientists, engineers, and astronauts, all keeping the same secret for decades. This conspiracy would require cooperation between mortal enemies during the Cold War. Communist and capitalist nations working together to maintain the same lie, and hundreds of thousands of people never breaking their silence despite the fame and fortune that would come from exposing the truth. It's absurd. The simplest explanation is the correct one. Earth is a sphere, because that's what we observe. Now, let's move beyond this nonsense and explore what shape Earth actually is. Now that we've established Earth is definitely not flat, let's talk about what it actually is. You've probably heard Earth described as a sphere. That's a good first approximation, but it's not quite right. Earth is an oblate spheroid, which means it's a sphere that's been squashed slightly at the poles and bulges at the equator. The equatorial diameter is about 43 kilometers larger than the polar diameter. That might not sound like much on a planet 12,742 kilometers across, but it's significant enough to affect everything from satellite orbits to the weights of objects at different latitudes. Why does Earth bulge? The answer is rotation. Earth spins on its axis once every 24 hours, completing one full rotation. This spin creates centrifugal force, which isn't actually a real force in physics, but rather the tendency of rotating objects to move outward from the center of rotation. Think about a pizza maker spinning dough. As the dough rotates, it spreads outward, creating a wider, flatter disk. Earth does the same thing, though much more subtly. The material at the equator is moving faster than material at the poles because it has to cover more distance in the same 24-hour period. At the equator, the surface moves at about 1,670 kilometers per hour. At the poles, it's essentially zero. This rapid movement creates an outward push at the equator, counteracting gravity slightly and causing the planet to bulge. The effect is balanced against Earth's gravity and its structural strength. If Earth were liquid, it would bulge more. If it spun faster, it would bulge more. As it is, we get an oblate spheroid with an equatorial bulge of about 21.5 kilometers compared to a perfect sphere. Mount Chimborazo, the highest point on Earth? Everyone knows Mount Everest is the tallest mountain on Earth, right? Its peak reaches 8,849 meters above sea level, higher than any other point on land. But here's a fun fact that exploits the equatorial bulge. Mount Chimborazo in Ecuador is actually the farthest point from Earth's center. Chimborazo's summit is only 6,263 meters above sea level, over 2,500 meters lower than Everest. But because Chimborazo sits almost exactly on the equator, where Earth bulges outward, its peak is about 2,168 meters farther from Earth's center than Everest's peak. If you were trying to get as far from Earth's center as possible while standing on land, you'd go to Chimborazo, not Everest. And if you were launching into space, you'd want to launch as close to the equator as possible to take advantage of Earth's rotational speed. That's why space agencies like NASA and ESA launch from Florida and French Guiana rather than higher latitudes. Weight variations across the globe. Here's something bizarre. You weigh less at the equator than at the poles. Not by much, less than 1%, but the difference is real and measurable. Two factors cause this. First, you're farther from Earth's center at the equator due to the bulge, and gravity weakens with distance. Second, the centrifugal effect from Earth's rotation counteracts gravity more at the equator than at the poles. If you weigh 70 kilograms at the North Pole, you'd weigh about 69.5 kilograms at the equator. It's a small difference, but it's there. Olympic officials actually account for this in some events. A pole vaulter jumping in Mexico City gains a slight advantage from lower gravity compared to jumping in Stockholm, though altitude plays a bigger role than latitude in that specific example. How we measured the bulge. The equatorial bulge was first calculated in the 17th century through expeditions that measured the length of a degree of latitude at different locations. French scientists traveled to Ecuador and Lapland to measure arcs of meridian, proving that Earth was indeed flattened at the poles. Modern measurements use satellites. By tracking how satellites orbit Earth and how their orbits change over time, we can determine Earth's exact shape with extraordinary precision. GPS satellites, laser ranging, and radar altimetry have mapped Earth's shape down to centimeter-level accuracy. These measurements confirm the oblate spheroid model and reveal even more complex variations in Earth's shape that go beyond a simple mathematical description. Earth's shape isn't constant. It changes over time, and some of these changes happen faster than you'd think. Tidal deformations. Earth breathes. Most people know the moon causes ocean tides, but did you know it also causes tides in Earth's crust? The solid ground beneath your feet rises and falls by about 30 centimeters twice a day as the moon's gravity pulls on the planet. This is called earth tide or bodily tide. The moon's gravity creates a tidal bulge in Earth itself, just like it does in the oceans. As Earth rotates under this bulge, any given point on the surface rises and falls. You can't feel it happening because everything around you, including buildings and mountains, moves together. The sun also creates earth tides, though only about half as strong as the moon's. When the sun and moon align during new and full moons, their tidal effects combine, creating slightly larger deformations. These tidal flexings dissipate energy through friction, very gradually slowing Earth's rotation. Hundreds of millions of years ago, days were shorter. In the distant future, they'll be longer. Earth's shape is constantly flexing under gravitational forces, like a stress ball being squeezed and released. Seasonal changes. Earth's shape changes with the seasons as atmospheric mass redistributes. During summer, in the northern hemisphere, the atmosphere warms and expands, creating a very slight increase in Earth's oblateness. During winter, the atmosphere contracts, The same happens with water. Snow and ice accumulate in winter, redistributing mass from oceans to land. Spring melting returns this water to the oceans. These seasonal mass movements actually change Earth's rotation rate very slightly, making days fractionally longer or shorter depending on the time of year. The differences are measured in milliseconds, but they're real. Earth's moment of inertia changes as mass moves around, affecting rotation speed, the same way a figure skater spins faster when pulling their arms in and slower when extending them. Long-term changes. On longer timescales, Earth's shape changes due to isostatic rebound. During the last ice age, massive ice sheets covered much of North America and Europe, weighing down the crust beneath them. When the ice melted about 10,000 years ago, the crust began slowly springing back. And it's still rising today. Scandinavia is rising by about 1 centimeter per year. The Great Lakes region of North America is also rebounding. This process will continue for thousands more years before the crust reaches equilibrium. Meanwhile, other areas are sinking. The Mississippi Delta is subsiding as sediment compacts. Venice is slowly drowning as the land beneath it settles. These vertical movements change Earth's shape in measurable ways. Climate change and Earth's shape. Modern climate change is affecting Earth's shape in detectable ways. As polar ice melts, mass moves from the poles toward the equator, changing the planet's moment of inertia and affecting its rotation. Studies have shown that ice loss from Greenland and Antarctica is measurably changing Earth's gravitational field. Satellites that measure gravity can detect these changes, mapping where mass is being lost and gained across the planet. The redistribution of water also affects sea level in complex ways. Because Earth's gravity field is changing as ice melts, the ocean doesn't rise uniformly. Some regions experience more sea level rise than others, depending on the changing gravitational pull of ice sheets and the deformation of the crust beneath them. Now we get to the really interesting part. Earth isn't just an oblate spheroid. It's much stranger than that. The true shape of Earth is described by something called the geoid, an irregular surface that represents what sea level would be if it could pass through all continents. It's the shape that Earth's gravity field creates, and it's lumpy, bumpy, and asymmetric in fascinating ways. Gravity is not uniform. Here's the key insight. Gravity isn't the same everywhere on Earth. The strength of gravity at any point depends on several factors, including distance from Earth's center, local geology, altitude, and the distribution of mass in the surrounding area. Dense rocks create stronger local gravity. Mountain ranges add mass above the surface, but they're typically less dense than the mantle below and often have roots of low-density material extending down into the crust. Ocean trenches represent missing mass. All of these factors create variations in gravitational pull. The geoid represents an equipotential surface, meaning it's a surface where gravitational potential is constant everywhere. If you could theoretically let water flow freely through all of Earth's crust and mantle, it would settle at the geoid surface. Every point on the geoid has the same gravitational potential energy. The lumpy potato Earth. When you visualize the geoid, it looks like a lumpy potato. Some areas bulge outward, others sink inward, creating an irregular shape that deviates from a perfect oblate spheroid by up to 100 meters in places. One of the most dramatic features is the Indian Ocean geoid low, an area south of India where the geoid dips about 106 meters below the reference ellipsoid. This represents a region of unusually low gravity, possibly caused by ancient remnants of subducted ocean floor deep in the mantle. Conversely, there's a geoid high near Iceland and another near New Guinea, where the surface bulges upward. These are regions of higher gravity, likely due to dense material in the upper mantle or unusual crustal structures. The geoid is constantly being refined as we make more precise measurements of Earth's gravity field. Satellites like GRACE, GOSI, and CHAMP have mapped Earth's gravity with unprecedented detail, revealing the complex interplay between surface features, crustal thickness, mantle density, and core dynamics. Why the geoid matters. Understanding the geoid is crucial for several reasons. First, it's the reference surface for all elevation measurements. When we say a mountain is 8,000 meters high, we mean 8,000 meters above the geoid, not above a mathematical spheroid. Second, it's essential for navigation. GPS satellites need to account for the geoid to provide accurate positioning. Modern GPS receivers have geoid models built in, converting between ellipsoidal heights measured from space and orthometric heights we use on the ground. Third, it tells us about Earth's interior. The shape of the geoid reflects the distribution of mass inside the planet, including things we can't directly observe, like mantle convection patterns, crustal thickness variations, and core dynamics. It's like an X-ray of Earth's interior created by gravity. Measuring the geoid. Historically, surveyors measured the geoid using gravity meters, instruments that precisely measure gravitational acceleration. They'd take measurements at thousands of locations, build a network of known gravity values, and interpolate between them to create a geoid model. This changed with satellite gravimetry. The GRACE mission, launched in 2002, consisted of 2 satellites flying in formation. By measuring tiny changes in the distance between them as they passed over regions of varying gravity, GRACE mapped Earth's gravity field with extraordinary resolution. GOSI, launched in 2009, took a different approach. Flying in an extremely low orbit and using ultra-sensitive accelerometers to measure gravity directly. It created the most accurate geoid model ever, resolving features as small as 80 kilometers across. These satellites revealed that Earth's gravity field is far more complex than anyone imagined, with intricate patterns reflecting everything from mountain ranges to ocean currents to groundwater depletion. Mass concentrations. MASCONs. Some of the most interesting features in Earth's gravity field are mass concentrations, or MASCONs, regions where gravity is measurably stronger than expected. These were first discovered on the Moon, where large impact basins filled with dense basaltic lava create positive gravity anomalies. Earth has its own MASCONs. The Hudson Bay region of Canada shows a negative gravity anomaly, still recovering from the weight of ice sheets that melted thousands of years ago. The Hawaiian Islands create positive anomalies due to the massive amount of volcanic rock piled on the ocean floor. Some MASCONs reveal ancient geological events. The Chicxulub impact crater in Mexico, which contributed to the dinosaur extinction 66 million years ago, shows up as a subtle gravity anomaly, even though the crater is completely buried under kilometers of sediment. Tracking changes in ice and water, GRACE revolutionized our ability to monitor changes in Earth's mass distribution over time. By comparing gravity measurements month by month, scientists can track the movement of water around the planet. The data shows ice loss from Greenland and Antarctica with remarkable clarity. As ice melts, local gravity decreases, and GRACE detects this. Between 2002 and 2016, GRACE measured ice losses of about 280 billion metric tons per year from Greenland and 120 billion metric tons per year from Antarctica. The satellite can also detect groundwater depletion. Aquifers in California, India, and the Middle East are being drained faster than they're replenished, and GRACE sees the resulting decrease in mass. This information is invaluable for water resource management. Even large floods show up in GRACE data. When massive flooding occurred in the Amazon basin, GRACE detected the redistribution of water mass across South America. Mantle convection and deep Earth structure. The geoid also reveals processes deep within Earth's interior. Mantle convection. The slow churning of rock in Earth's mantle that drives plate tectonics creates long wavelength variations in the gravity field. Hot mantle plumes, rising columns of buoyant rock from deep in the mantle, create subtle geoid lows because they're less dense than surrounding material. Cold, descending slabs of subducted crust create geoid highs because they're denser. By studying these patterns, geophysicists can infer what's happening hundreds of kilometers below the surface, mapping the convection cells that drive continental drift and volcanic activity. The core's influence. Even Earth's core affects the geoid, though very subtly. The liquid iron outer core is denser than the rocky mantle above it, creating a strong gravitational signal. Movements in the core, driven by convection and Earth's rotation, may create tiny variations in the gravity field, though these are extremely difficult to measure. The boundary between the core and mantle isn't smooth. There are structures at this boundary, possibly remnants of ancient subducted slabs or accumulations of dense material, and these affect Earth's gravity field in ways we're only beginning to understand. GPS and the geoid. Every time you use GPS, you're relying on an accurate model of Earth's shape. GPS satellites orbit about 20,000 kilometers above Earth, transmitting signals that your receiver uses to calculate position. But those satellites are measuring your distance from a reference ellipsoid, a simplified mathematical model of Earth's shape. To convert this ellipsoidal height into a useful elevation, like meters above sea level, GPS receivers need a geoid model. Without it, your altitude reading could be off by tens of meters depending on where you are. High-precision GPS applications, like surveying, aviation, and autonomous vehicles, require extremely accurate geoid models. A surveyor laying out a construction project needs to know elevation to centimeter accuracy. An aircraft on final approach needs to know its height above the ground. Both depend on understanding Earth's real shape. Satellite orbits. Earth's oblateness affects satellite orbits. The equatorial bulge creates an additional gravitational force that causes satellite orbits to precess, meaning the orbit plane rotates over time. This precession is actually useful. Sun-synchronous satellites, which pass over each location at the same local solar time, exploit this effect. By choosing the right orbit inclination and altitude, engineers can make the orbit precess at exactly the right rate to match Earth's orbit around the Sun, keeping the satellite's ground track aligned with the Sunday. Weather satellites, Earth observation satellites, and many scientific missions use sun-synchronous orbits, all made possible by Earth's equatorial bulge, ocean currents, and sea level. The geoid is crucial for understanding ocean dynamics. Sea level doesn't follow a simple spheroid. It follows the geoid, with variations of up to 100 meters due to gravity anomalies. But the actual ocean surface deviates from the geoid due to currents, winds, temperature, and salinity. Satellite altimeters measure the ocean surface height, and by subtracting the geoid, oceanographers can determine ocean topography, the hills and valleys in the ocean surface created by currents and eddies. For example, the Gulf Stream creates a slope in the ocean surface as water piles up on one side of the current. This slope, only about 1 meter over 100 kilometers, drives the current's flow. Understanding it requires knowing both the geoid and the actual sea surface height. Engineering and construction. Large engineering projects must account for Earth's curvature and the geoid. The Channel Tunnel between England and France required surveyors to account for both the curvature of Earth and the local geoid when aligning the tunnel from both ends. The Large Hadron Collider at CERN, a 27-kilometer ring, had to be constructed with Earth's curvature in mind. If engineers had assumed a flat surface, the two ends wouldn't have met properly. Even smaller projects like bridges, highways, and railway lines must consider Earth's shape when spanning long distances. Water flows downhill following the geoid, so drainage systems and canals need accurate elevation data. Chapter 8. Climate and Environmental Monitoring. 51-0. 57-0. Ice sheet monitoring. Understanding Earth's shape is critical for monitoring climate change. Satellites measure ice sheet thickness by bouncing radar or laser pulses off the surface and timing their return. But to convert these measurements into actual ice thickness and mass, you need to know the height of the underlying rock, which requires an accurate geoid model. Satellites like ICESat-2 measure surface elevation changes over Greenland and Antarctica with millimeter precision. Combined with gravity data from GRACE, scientists can track both ice volume and mass, determining whether ice loss is due to melting or dynamic processes, like glaciers flowing faster. The data is sobering. Greenland is losing ice faster than at any time in at least 12,000 years. Antarctica's ice loss has tripled since 2012. These changes are reshaping Earth's gravity field and contributing to sea level rise worldwide. Sea level rise and local impacts. Sea level rise isn't uniform. When ice melts in Greenland, sea level doesn't rise by the same amount everywhere. Near Greenland, sea level actually falls because the ice sheet's gravitational pull decreases, allowing water to flow away. Far from Greenland, in the southern hemisphere, sea level rises more than the global average. This phenomenon, called gravitational fingerprinting, means that different regions experience different rates of sea level rise, depending on where ice is melting. Understanding it requires detailed knowledge of Earth's gravity field and how it changes as ice melts. Coastal communities need these projections to plan for the future. Should they build sea walls? Relocate infrastructure? Understanding local sea level rise requires understanding Earth's shape and how it's changing. Earthquake monitoring. Large earthquakes literally change Earth's shape. The 2011 Tonsohoku earthquake in Japan was so powerful, it moved the main island of Honshu about 2.4 meters eastward and altered Earth's rotation by about 1.8 microseconds. Satellites detected these changes. GPS stations throughout Japan recorded the ground displacement in real time. GRACE measured changes in the gravity field as mass redistributed. This data helps seismologists understand the earthquake mechanism and improve models of tectonic plate interactions. Even smaller earthquakes leave subtle signatures in Earth's gravity field and shape that satellites can detect, providing a new tool for studying seismic hazards. So, what shape is Earth? The answer is more complex than most people realize. It's definitely not flat. That idea was proven wrong thousands of years ago and has been thoroughly demolished by modern observations. It's not a perfect sphere either. Earth bulges at the equator and flattens at the poles due to rotation, making it an oblate spheroid. But even that description isn't complete. Earth's true shape is a geoid, an irregular surface defined by gravity, lumpy and asymmetric, reflecting the complex distribution of mass in the crust, mantle, and core. This shape changes constantly due to tides, seasons, ice melting, groundwater movement, earthquakes, and mantle convection. Understanding Earth's real shape isn't just academic curiosity. It's essential for GPS navigation, satellite operations, climate monitoring, sea level projections, engineering projects, and countless other applications. The more precisely we map the geoid, the better we can understand and manage our planet. Modern technology has given us an unprecedented view of Earth's shape. Satellites circle overhead, measuring gravity, surface height, ice thickness, and ocean topography with extraordinary precision. We can track changes month by month, year by year, watching the planet respond to natural cycles and human influences. What we've learned is humbling. Earth is a dynamic, living planet, constantly shifting and changing beneath our feet. The ground isn't static, sea level isn't uniform, gravity varies from place to place. Nothing is as simple as we once thought, and yet, despite all this complexity, we can describe it, measure it, and predict it with remarkable accuracy. We've gone from ancient astronomers using shadows to calculate Earth's size, to modern scientists mapping gravitational anomalies from space. In a few generations, we've transformed our understanding of the planet we call home. The next time someone asks you what shape Earth is, you can tell them it's not a simple answer. It's an oblate spheroid with an irregular geoid surface that varies by up to 100 meters, constantly deforming under tidal forces, changing with the seasons, responding to ice melt and groundwater depletion, affected by earthquakes and mantle convection, measured by satellites and mapped with precision down to centimeters. Or you can just say it's lumpy. That works too. Earth's real shape has finally been revealed, and it's more fascinating, more complex, and more beautiful than a simple sphere or disk could ever be. It's the shape of a planet shaped by physics, geology, and the intricate dance of forces that have operated for billions of years. And we're standing on it right now. A lumpy, spinning, wobbling, breathing planet hurtling through space. Pretty amazing when you think about it. Thanks for watching. And remember, the Earth is round. Very, very round. Just not perfectly round.